Hello, today we're going to talk about going into S mode. So S mode is called supervisor mode because what we're going to do is move ourselves down a level from where we were in the OS blog. In the OS blog, we started at machine mode. It means we had full control over the machine and the machine was our oyster, for lack of a better term. If you look at your screen, what you're seeing is the OpenSBI on GitHub. And if you look at this, this is the OpenSBI that runs on RISC-V. And what it is it's a binary encoding on how you can actually interface with something sitting at the machine mode. For lack of a better term, it's a BIOS, like in the Intel AMD processors, that sits on top of RISC-V. So usually what happens is we transfer control to a certain memory address and we just take control from there. We're in machine mode and we just decide what we're going to do straight up. However, like in BIOS mode, you jump to a certain location, it does a whole bunch of initialization routines, and then finally gets into your operating system, your bootloader. So that's essentially what this is as well. So SBI stands for Supervisor Binary Interface, and essentially where at the user level you have the application binary interface so that a high-level language and a low-level language can communicate with each other. In this case, an SBI allows us to communicate with the machine using our operating system. So our operating system is now abstracted away just a little bit from the hardware device. In this case, you can see there's a whole bunch of different lists of error codes, structures for the errors, and how this is going to work. So essentially what happens is we fill in a bunch of registers with, here's the utility that I want you to do, almost like a system call. In fact, this is a system call. And then we execute eCall, which is a system call. So if we're in the SBI mode, or in the supervisor mode, what's going to happen is we're going to jump to machine mode and hit the trap vector from there. The trap vector for the machine mode is controlled by OpenSBI. And OpenSBI will run the utilities that needs to be done for that sort of thing. So as you can look here, there's a whole bunch of, this is the specification. There's two different places you need to look for here. So OpenSBI, if you do RISC-V/OpenSBI, that's actually the source code for OpenSBI. But if you do RISC-V-SBI-doc, that's actually the documentation for OpenSBI. As you can see here, well, not OpenSBI, but SBI. So OpenSBI is an implementation of this document. So you can see you have base functionality, extension ID 0x10. It tells you exactly what registers to put these sort of things in. But you can see these different things that we have. So one of the things that you'll notice is that we have something like M vendor ID, M arc ID, architect ID, and implementation ID. Now what happens is in machine mode, we have access to all the registers, M registers, S registers, so the machine mode registers, the supervisor registers, and nothing will be restricted from us to use. However, in supervisor mode, we are no longer allowed to access any of the machine mode registers. So what does that mean? So one of the biggest things that means is, number one, we can't get our own heart ID. So the core ID is stored into a register called mHeart ID. Heart stands for hardware thread, RISC-V's term for a core. And essentially what that means is we actually have to follow the core around. So there's a pretty neat way that we can do that inside of here, but it just means that we actually have more things to do. Now, in some operating systems, they store it into a register like the thread pointer, but users can actually access the thread pointer, change that sort of stuff. So it's not the best way to go about this. Actually, they've added something to it. System reset ID. That never used to exist, so that's new. Used to stop here. So as you can see here, the nice thing about OpenSBI is we actually have a heart management system. So heart stands for hardware thread, like I said, and heart ID no longer exists. So we are not allowed to see what our heart is. So what will happen is OpenSBI will boot. It goes through a lottery. Essentially, it's a random roll of the dice and says, all right, core 3, you are the bootstrap core. And then it runs and boots your operating system at a certain memory address. So OpenSBI, whenever the core, whenever this board over here, you can't see it. I'm about to rip it off. There we go. This board right there. So that's the High Five Unleashed. That's the expensive board. But the High Five Unleashed, what will happen is it'll go through its own routines. It has its own bootloader. It jumps to a certain memory address, where OpenSBI will be located. So OpenSBI runs its routines, gets all the trap vectors set up, and then finally jumps to your operating system, or in this case, my operating system. So what will happen is it goes to your operating system and then figures out, all right, now we start running from there. However, when we go to your operating system, we are in what's called supervisor mode. Supervisor mode is a mode below machine mode, meaning we don't have access to the full architecture. So we have to use this. So to start, so this thing has 5 cores. So it has core 0, which is what's called the monitor core. It's just a supervisor core for all the other cores. And then cores 1 through 4, the hearts 1 through 4, are essentially your compute cores. And it's kind of interesting the way this works, because whenever we're trying to trigger interrupts and things like that, we actually have to configure each core and the mode of each core or each heart. I don't know which one I should be saying, but anyway, most people know them as cores. In the RISC-V world, we know them as hearts. So there you go. Anyway, what's going to happen in this case is to start processing on a core. So what happens is OpenSBI will choose, like I said, the lottery. All the other cores are parked, meaning they're in usually a loop that says wait for an interrupt, and it just stops the core. However, what we need to do is we need to be able to start a core and say, here's an application that we want you to start. So SBI Heart Start is actually what we're going to use for that. As you can see up here, Heart Start takes a heart ID. So we actually have to, as the operating system, configure, okay, which ones are legitimate cores and which ones are not. And we can use get status to actually see which cores we have available to us and which ones we can actually identify here. Then we have a start address. That's a physical address wherever it's going to start executing. And so generally what you do is you do the starting address somewhere in your kernel, and then the kernel will set everything up, the registers that need to go to user mode or something like that, set everything up and go into user mode from there. So this privilege mode right here allows you to actually set the privilege mode to user mode if you want to. However, getting everything done from there is going to be difficult, like setting the SATP register for the MMU. You're not going to be able to do that if it jumps directly into user mode. So I recommend, I don't know, that's what I've done anyway. So what I've done is I put privilege mode to 1, which is supervisor mode, and then jump to a kernel routine, which will actually start the heart. So the nice thing about that is the heart ID. So as you can see, upon execution from start address, A1 contains the privilege, and somewhere in here, unless it's changed, but it used to say A0 contains the heart ID. There we go. So A0 contains the heart ID, A1 contains the privilege mode. So whenever we jump into there, if you don't know anything about RISC-V, A stands for argument. So the very first argument, that's C ABI right there. So in C, C++, Rust, all that sort of stuff, the very first argument that you pass into a function, so we can actually do this in a high level language, it's going to be the heart ID. Remember what I said is the M heart ID, the register is a machine mode register. We don't have access to it. So we actually have to follow this around, the heart ID. And generally what you do is you would put that in sort of the context of the processor running on that heart. And so that way there you can keep track of the heart. So that is a little bit of an issue whenever it comes to running supervisor mode, is that you have to keep track of your hearts. There's no way you can just say, I forgot who I am. Who am I? In machine mode, in my machine mode operating system, we can just query the M heart ID and say, oh, that's who you are. However, in supervisor mode, you can't do that. Now, one thing that is nice about this is it sort of makes managing your hearts easy. You have start, you have stop, and then you have status. Stop just means if you're running in that heart, it will stop. Generally, what happens is if you're running a user mode application, you'll set a timer somewhere in the future so that that user space application can run. And then whenever the timer hits, it'll hit your trap, go into supervisor mode, and then you say stop the heart. And then you can context switch, change to another process or whatever it needs to happen. So a couple of things that are interesting in there, as you saw, is the first one is this is growing. In fact, even before I did this, system reset extension did not exist. Now that's kind of nice because very difficult to see how you can reset this because every single board is a little bit different on how you want to be able to reset it. Some of them can't be reset. You actually have to physically reset it. And so this is kind of nice to be able to do this. But I haven't tried it, so we'll see if that works. Shut down, cold reboot, warm reboot. We'll see what that does later. So another thing about this is OpenSBI is a kind of a interesting, it's a work in progress. Let's just put it that way. So as you see, 14 days ago, well, I guess I don't keep up with this as much as I'd like to. But anyway, so in this case, you can see we have different platforms in here. So these are the different platforms that we have available at the OpenSBI. So Quick Emulator Vert, that's what I use a lot, as well as the Sci5 FU540. So that's the Hi5 Unleashed. That has the 5 cores, things like that, and it allows a fairly easy way to manage that. There's a couple of other things in there. And finally, we have what's called, not platform, firmware. There we go. So there's many different ways we can actually jump to your operating system. So the operating system, the OS, or the OpenSBI, what it'll do is it'll choose a method to get into your operating system. One of those methods is it can jump to just a specific memory address. And that's what I use for Vert. And then we can use payload so that actually your kernel can actually be combined into OpenSBI. So it's just one big long kernel. The OpenSBI is at the top. Then you have what's called the payload, starts at a different memory address, and your kernel is stored in the same binary. So you have one binary that stores all of them. I use jump for that because in Quick Emulator, as you can see down here, The new quick emulators have a BIOS specification. So let's take a look at that. Okay, so if we take a look at this, you can see we have dash BIOS and then SBI.bin. That's essentially the open SBI that it's going to be. And then we can actually run our kernel at the end. So it gives us two different things that we can actually to specify inside of here. And it's kind of nice because open SBI changes fairly frequently. So it's nice to, okay, I have my kernel over here, I have my SBI over here, and they're kept separate. However, in some boards, we need to combine those into, like I said, one kernel and then flash it onto like an SD card. So for example, on this High5 Unleash, there's a specific partition on your SD card and you place your kernel in there. And so generally what you do is you set it as a payload, one big package, you DD it in there. So byte by byte copy into the SD card. And that's actually how you get it into there. So there are a few things in here that aren't working exactly like I planned. So one of those things is this portion right here. So this is what's called the PLC, Platform Level Interrupt Controller. A platform level interrupt controller means you have interrupts per core, but the platform level, I think there's a diagram in here actually. Let's see, maybe not. I guess I should edit this so you don't see me just scrolling around, but whatever. I guess I should edit it so you see me not find what I need here. But anyway, so the platform level interrupt controller controls what's are called external interrupt. There's 3 pins on the CPU. You have a timer pin, a software interrupt pin, and then an external interrupt pin. Those are core level. So each heart has those 3 pins on them. So you can actually interrupt each core individually. So a timer, you can control the timer through what's called the CLINT, the core local interrupt controller, and it's fairly simple. There's only 3 things that it does. It has a timer trigger, and then a software interrupt. If you write a 1 to it, it causes a software interrupt. The external interrupt has a separate controller called the PLC, the platform level interrupt controller. You can see it has a whole bunch of different sources here. The level 2 cache, UARTs, SPI, serial peripheral interface, GPIO, DMA, and even Ethernet's in there. So this, you can actually prioritize your interrupts. You can enable them, you can disable them. So you can see you control it by using MMIO. So it's most PLCs are set at 0C00. Most CLINTs are stored at 0200. And so those memory addresses have been fairly consistent across RISC-V boards. Just like the boot address, which is 8,000,000, that's pretty common across most of these boards. I haven't seen one that isn't 8,000,000. However, if you're using OpenSBI, what's going to happen is OpenSBI will boot at 8,000,000, then usually come in at around 8,002,000. So in this case, you can see one of the issues that I had when I was programming this is the monitor core on here only runs in M mode. So remember, it has 5 cores, but the first core, core 0, heart 0, only runs in M modes. There is no supervisor mode. And notice that you can actually control the interrupt enables at which level. So for example, if I want to interrupt, so what happens is what this is going to do is it's going to interrupt your CPU, and it will go into a specific, it'll trigger that external pin, and then it'll go to a specific trap handler. Now the trap handler I want is going to be either S mode or M mode according to this. And so that's essentially what's going to happen whenever we go into it, is which level do we want to trigger this at, or to be able to trigger. So for example, if I'm in N mode, I don't want it to be able to trigger on S mode to be able to interrupt me whatever I'm doing inside of machine mode. We just want it to stay pending, and then whenever we go back into S mode, then we can hit the trap whenever it comes. So the interesting part about here is notice this starts at C002,000. So that's where the M mode starts here. And then heart 1 starts at 2080, and then 2100, then 2180. So the jog and the strides are a little bit different because you would expect that M mode would be at 2000, S mode for heart 0 would be at 2080. So each one of these has a little bit of stride to them. And notice that between heart 1 M mode and heart 1 S mode, there's a 0x80. So there's a 256 byte difference between the two. All right, so what's going to happen whenever we do that? Well, the problem that we're going to see is, in this case, actually, wait a minute. Yeah. All right. So anyway, the issue that we're going to face here is our strides are going to be different depending on the core configurations. Not all cores have supervisor mode. Not all cores have, well, all cores have machine mode. That's required in the specification. But as you can see here, because there's no supervisor mode in heart 0, it makes all of our offsets a little bit different. And so if I want to find out where S mode is, I actually have to start at 0 mode. Remember that there is no S mode for heart 0. Move to M mode. So it goes M to M to S. Then it goes M to S, M to S, M to S. As you can see here, heart 2, M to S, M to S, M to S. And so as soon as I get to heart 1, then everything is consistent. I have a consistent jog, but because of the different ways we have software, and this is only evident that I've seen inside of something where we actually implement S mode. So if we just had an M mode controller like the High Five 1, if we only had that, then this wouldn't even matter. We just configure it for whatever core. I don't even remember how many cores the High Five has, the High Five 1. But we just configure that core. We set in machine mode. Here's where we want your trap, things like that. So those are the interesting tidbits that I'm coming across that aren't working so well for me, just moving us from the machine level to the supervisor level. So number 1, we don't have access to all the registers. Number 2, everything now starts with an S, so that's a little bit different. So instead of M status, now you have S status for supervisor status register. Number 3, your interrupt controllers now have modes: machine mode, supervisor mode, machine mode, supervisor mode. So now when we're configuring one of these U type cores, these application processors, now we have more things that we have to consider in this case. So unfortunately, that's what's starting to happen. You can see here that they're actually doing deliberate restrictions. So our operating system is starting at supervisor mode now. So as I start moving more things into supervisor mode, I'm pretty sure more things are going to start popping up that I didn't even think of. And that gives us an opportunity for another video. Thanks for watching. Have a good day.